This is the Goddess of Science Physics, and today we're going to do part 3 of my momentum series. And today we're going to talk about the conservation of momentum. So, the main idea of this section is the law of conservation of momentum says that in the absence of some external force, the momentum of a system remains unchanged. And we need to talk about what constitutes a system here. As long as it's like kind of contained, like you inside a car, that's a contained system. A car that hits you from behind is not part of your little contained system. Okay. So when you're firing a cannon, we talked about firing a cannon before in chapter 6 about why it recoils. But if you look at the momentum of the cannon and the cannonball before firing, it's going to be 0 because neither one of them are moving. That's not really hard to get your head around, excuse me. Because it's not moving, obviously, momentum has to be 0. But after you fire that cannon, the net momentum, now momentum is a vector quantity, so direction matters. The net momentum is 0 because the momentum of the cannon is equal and opposite that of the cannonball, the momentum of the cannonball. Okay, so after firing, the net momentum is 0 because the momentum of the cannon is equal but opposite to the momentum of the cannonball because they're going in different directions. So there we go, blam. I don't know what cannon actually fires and it says blam, but okay. So momentum, it has both direction and magnitude. It is a vector quantity because it contains velocity, which is also a vector quantity. Both the cannonball and the recoiling cannon gain momentum, but because the recoiling cannon is going in the opposite direction, its momentum that it gains is negative, and then the cannonball's is positive, or vice versa. It doesn't really matter, but they have the same momentum, but just going in different directions so that they cancel each other out. The cannon-cannonball system gains none overall. It just takes the momentum and splits it between the two, and as it's splitting it between the two, one's positive, one's negative. Positive 4, negative 4, you end up with 0. There's no change in momentum. So the momentum of the cannonball and the cannon are equal in magnitude but opposite in direction. That's the same thing happens not with momentum but with terminal velocity. When you're falling and you reach terminal velocity, the force of friction is exactly equal and opposite to the force of gravity pulling you down. So you stop accelerating. So that's an example of two things that add out to give you 0. This is another example of them. There's no net force acting on the system when momentum is conserved. It happens within the system, the cannonball system. So if there's no net force acting, then there can't be an impulse acting on the system, because remember, impulse, that weird J, equals force times time. If force is 0, then there can be no impulse, which means there's no change in momentum. No net change in momentum. Each object in the system, the cannon gains some momentum, the cannonball gains some momentum, but when you put it together as an entire system, there's no net change because they're going in opposite directions, which means they cancel each other out. So the momentum of the system can't change unless there's acted on by an external force. Law of conservation of momentum says that it's not going to change. We've had, I don't know if you remember, but last year you might have talked about the law of conservation of matter. When you're balancing equations, you got to have the same number of atoms on one side as on the other side. If you didn't learn about that last year in biology, that's fine. but you're going to run across a lot of these law of conservation of something. There's law of conservation of mass, law of conservation of matter, law of conservation of momentum, law of conservation of energy. All of those, whenever you have a law of conservation of whatever, it just means that before something happens and after something happens, whatever it is going to be equal. So the momentum you have before something happens is going to be exactly the same as the momentum after. So in the cannonball system, it has no momentum when it's starting out because it hasn't been fired yet, nothing's moving. So the net momentum afterwards has to also be zero. Even though you got two moving things, their product of mass times velocity is going to cancel each other out because they're going in opposite directions. Okay, if a quantity in physics doesn't change, we say it's conserved. So that's why you have the law of conservation of whatever, momentum, mass, energy, that kind of stuff. Okay, well, that was a short one. So thanks for joining me. Have a great day.